Since early Greek philosophers, matter was thought to have a physical limit. In 1808, John Dalton formalized this as the first modern atomic theory. The concept was built into the name itself. The Greek word atomeo translates to uncuttable or non-divisible. Dalton's theory regarded these ultimate particles as the fundamental building blocks of all matter. This model assumed the parmunu was a solid, impenetrable unit containing no internal parts or smaller constituents. For nearly a century, this assumption functioned as a conceptual wall, making it impossible for scientists to explain how matter could interact with electricity. The evidence that would eventually challenge Dalton's solid sphere model came from the study of static electricity. When a glass rod is rubbed with silk, or a comb is passed through dry hair, it begins to attract small pieces of paper. If atoms are truly solid and indivisible, they should remain electrically neutral. The existence of a movable charge raised a critical question. Where does this electrical energy originate? Simple friction appeared to be stripping something away from the supposedly uncuttable atom. By the end of the 19th century, these observations suggested that the atom might possess an internal structure that scientists had yet to see. This macroscopic anomaly triggered a global race to identify the particles hidden inside the atom's architecture. In 1897, J.J. Thomson provided the first experimental proof of a subatomic particle. Using a cathode ray tube, Thomson generated a beam of energy in a vacuum. The beam traveled from the cathode and struck a screen, creating light. When an electric field was applied perpendicular to the path, the ray deflected toward the positive plate. This deflection identified the beam as a stream of negatively charged particles, which were later named electrons. By balancing the strengths of the electrical and magnetic fields, Thomson was able to measure the exact ratio of the particle's charge to its mass. Following this discovery, Robert Millikan used his oil drop experiment to quantify the exact electrical charge, E, of a single electron. Thomson found that these Rinovesh, or negative electrons, were a basic constituent of all atoms, regardless of the materials used in the tube. By isolating the electron, Thomson proved that the atom was not an indivisible unit, but a complex structure containing even smaller particles. Thomson's discovery led to the plum pudding model, which suggested electrons were scattered through a positive sphere. Ernest Rutherford set out to test this distribution. Rutherford fired high-energy, positively charged alpha particles at a sheet of gold foil only 100 nanometers thick. While most particles passed directly through the foil, a tiny fraction ricocheted at sharp angles. Some even bounced straight back toward the source. Rutherford compared the result to an artillery shell bouncing off a piece of tissue paper. The data revealed that the atom is mostly empty space, with nearly all its mass and positive charge concentrated in a tiny center. This center, the nabec, or nucleus, is where positively charged protons are located. Because a proton is approximately 2,000 times heavier than an electron, the nucleus accounts for almost the entire weight of the atom. Rutherford's experiment replaced the solid sphere with a model resembling a miniature solar system, defined by a dense, heavy heart. However, the mass of the protons did not match the total mass of the atom. A significant portion of the weight remained unexplained. In 1932, James Chadwick looked for an electrically neutral particle to resolve this discrepancy. By bombarding a beryllium sheet with alpha particles, Chadwick triggered the emission of a highly penetrating form of radiation. These particles were passed through electric fields and showed no deflection. They were electrically neutral. These particles, named neutrons, were found to have a mass nearly equal to that of a proton. Chadwick's discovery of the neutron completed the structural map of the atom's core. With these three particles identified, we can compare the properties that govern the behavior of all matter. The electrical balance is precise. Protons are +1, electrons -1. Neutrons carry zero charge. Mass distribution is equally stark. Protons and neutrons each provide 1 unit of mass, while the electron's contribution is considered negligible. As a result, the nucleus contains the atom's mass in a very small space, while the electrons occupy the vast surrounding volume. This combination of extreme density and extreme emptiness defines the internal environment of the atom. These particles define the identity of the elements. The atomic number is the count of protons, while the mass number is the total sum of protons and neutrons. Atoms of the same element with different numbers of neutrons are called isotopes, or samastonic. Because isotopes have the same number of protons and electrons, they show identical chemical behavior. Chemical properties are determined by the electrons moving in the outer shells, designated as K, L, M, and N. Breaking the atom apart through these experiments transitioned us from Dalton's solid sphere to a complex landscape of particles and fields constituting everything we see.